Long before the dawn of the 20th century, humanity's understanding of the cosmos was limited to the planets and celestial bodies visible from Earth with the unaided eye or through the earliest telescopes. The idea of other worlds, planets orbiting distant stars beyond our own sun, was a subject more of philosophical musing and speculative fiction than scientific certainty. It is difficult to overstate the profound shift in human perspective that came with the discovery of exoplanets, worlds orbiting stars far beyond our solar system. This moment marked a transformation in both astronomy and our understanding of our place in the universe. To truly appreciate this shift, we must travel back through the history of how we glimpsed our first hints of these hidden, distant worlds. For centuries, stars were understood as distant suns scattered across the night sky, but whether they harbored planets like our own was a question that remained unanswered. The tools simply did not exist to verify their presence. Philosophers and early astronomers suggested the possibility, but solid evidence was elusive. It was not until the late 20th century that technology progressed to the point where the existence of exoplanets, or extrasolar planets, could be confirmed. The story begins in earnest in the early 1990s, a period which many consider to be the dawn of exoplanet discovery. In 1992, scientists Alexander Wolszczan and Dale Frail announced a startling discovery: planets orbiting a pulsar named PSR B.1257+12. A pulsar is a highly magnetized, rotating neutron star that emits beams of electromagnetic radiation. The planets detected here were among the very first confirmed exoplanets, though they were an unusual case, orbiting an extreme, dead star rather than a normal star like our Sun. Though fascinating, the discovery did not ignite widespread excitement about habitable worlds, but rather opened the door to the possibility that planets might be more common in the universe than previously thought. Just a few years later, in 1995, the first exoplanet orbiting a main sequence star similar to the Sun was detected, dramatically changing the narrative. Michel Mayor and Didier Queloz, two astronomers at the University of Geneva, found an exoplanet around the star 51 Pegasi, located about 50 light-years from Earth. The planet, designated 51 Pegasi b, was a gas giant similar to Jupiter, but orbiting extremely close to its star, a so-called hot Jupiter. This discovery was monumental. It was the first world outside our solar system detected via the radial velocity method, observing the tiny wobble in the star's motion caused by the gravitational pull of the orbiting planet. What made this discovery particularly remarkable was that it shattered previous assumptions about planetary formation. Scientists had expected to find planetary systems similar in architecture to our solar system, where massive gas giants orbited far from their star. Yet, 51 Pegasi b was a massive planet tightly hugging its star, completing an orbit in just about 4 days. This suggested that the variety of planetary systems could be far more diverse than anyone had imagined. The late 1990s and early 2000s witnessed a rapid acceleration in exoplanet discoveries, fueled by technological advancements and the deployment of dedicated telescopes and instruments. Dozens of worlds were found by using increasingly precise methods, including radial velocity measurements and later, transit observations, where the slight dimming of a star's light indicated a planet passing in front of it. Each successive discovery brought new surprises: planets with extraordinarily eccentric orbits, multi-planet systems of exotic compositions, and worlds orbiting stars across different spectral types and ages. Slowly, the perception shifted from these objects being outliers or curiosities to the realization that planets are common, likely numbering in the billions in our Milky Way galaxy alone. But beyond mere numbers, the significance of these discoveries lay in a deeper question. Could some of these distant worlds harbor life? This question sparked a renewed enthusiasm, not just within the scientific community, but captured the public imagination worldwide. What did it mean to be a planet? Could any of these alien worlds support life, water, or even landscapes as diverse as those found on Earth? These inquiries would drive the next phases of exploration and discovery. The dawn of exoplanet discovery was not just a scientific revolution, but a cultural and philosophical milestone. It compelled us to reconsider our cosmic neighborhood, challenging Earth-centric views and inviting a more expansive understanding of planetary formation and evolution. The tale of these first glimpses beyond our solar system is a story of human curiosity, tenacity, and the relentless quest for knowledge. As the 21st century began, new tools were developed with even greater sensitivity and precision. Among them, space-based telescopes that would soon revolutionize our ability to detect these distant worlds, not just as points of light affecting their stars, but as worlds with measurable sizes, compositions, and atmospheres. This was the beginning of a new chapter, one that moved from discovery towards characterization, exploring mysteries of these exoplanets' nature, climates, and potential habitability. In this unfolding saga, the early discoveries serve as a foundation. They remind us of the unexpected cadence of scientific progress, where persistent observation and innovative techniques reveal hidden corners of the universe. The journey outwards, from the first confirmed exoplanets orbiting pulsars and nearby stars to the vast catalogs of alien worlds we now know, is an invitation to continuously expand our horizons, both literally and figuratively. In the next chapter, we will explore the remarkable methods astronomers have crafted to find these hidden worlds, ingenious ways of detecting what could once barely be imagined. How do we peer across the void of space and detect planets that are entirely invisible to even our largest telescopes? From subtle shadows cast during a transit to the gentle stellar wobbles detectable through precision instruments, these methods are the keys that unlock humanity's growing inventory of the cosmos' mysterious exoplanets. As we venture further into the captivating realm of exoplanets, it becomes essential to explore the ingenious methods by which astronomers have uncovered these hidden worlds. Unlike the planets in our own solar system, which can be directly observed through telescopes, exoplanets are often cloaked in darkness, invisible against the overwhelming brightness of their parent stars. For centuries, the possibility of other worlds orbiting distant suns was a tantalizing mystery. But only with the development of innovative detection techniques did those worlds become tangible realities. This section journeys through the varied and sophisticated approaches astronomers use to find these elusive exoplanets, revealing the delicate dance between light, gravity, and cosmic geometry that makes discovery possible. At the core of exoplanet detection lies the challenge that these planets are exceedingly faint and minuscule compared to their host stars. To put it in perspective, imagining an exoplanet visible beside its brilliant star is akin to spotting a firefly fluttering near a distant lighthouse. Direct imaging of exoplanets remains difficult and is typically limited to large, young, or widely separated planets, reflecting or emitting enough light to be discernible. Consequently, astronomers have employed indirect methods, inferring the presence of a planet from its effects on the star or from subtle changes in the star's light. One of the earliest and still most prolific techniques is the radial velocity method, sometimes called the Doppler spectroscopy method. This technique relies on the gravitational relationship between a star and its orbiting planet. As a planet circles its star, its gravity exerts a small pull, causing the star to move slightly in response. This movement is not visible directly, but affects the starlight itself. Thanks to the Doppler effect, the light from the star shifts subtly towards the blue end of the spectrum, as it moves towards Earth and shifts to the red when moving away. By carefully measuring these shifts using highly sensitive spectrographs, astronomers can detect the wobble in the star's motion, revealing the presence of one or more planets, as well as providing estimates of their masses and orbital properties. This method proved especially powerful in the late 20th century, leading to the first confirmed exoplanet around a sun-like star. However, the radial velocity method is most sensitive to large planets orbiting close to their stars, as these induce the most noticeable stellar wobbles. Detecting smaller, Earth-like planets using this method is incredibly challenging due to their faint gravitational influence. Another breakthrough came with the transit method, a technique that has revolutionized exoplanet hunting in the 21st century. The transit method simply observes the slight dimming of a star's light when a planet crosses, or transits, in front of it along our line of sight. This tiny dip in brightness, often less than 1%, is a hallmark of an exoplanet passing across the stellar disk and temporarily blocking a fraction of the light. The beauty of this method lies in its capacity to reveal a planet's size, as the amount of light blocked relates directly to the planet's diameter, and provide data on the orbital period by measuring the interval between successive transits. Groundbreaking space telescopes, designed exclusively for this purpose, such as NASA's Kepler mission, have employed the transit method to discover thousands of exoplanet candidates, dramatically expanding our catalog of alien worlds. The transit method also enables astronomers to study planetary atmospheres by examining the starlight that filters through those atmospheres during transit, offering clues about the chemical composition and possible habitability. Microlensing presents a less intuitive but equally fascinating avenue for exoplanet detection. This method exploits a phenomenon predicted by Einstein's general relativity, where the gravitational field of a star and its planets acts as a lens, magnifying the light of a more distant background star. When a planetary system aligns closely with this background light source, the planet's presence manifests as a distinctive blip in the brightening pattern. Though microlensing events are rare and random, surveys leveraging this approach have found planets even in otherwise inaccessible regions of our galaxy, including those orbiting faint or isolated stars. In addition to indirect detections, direct imaging is gradually becoming a more feasible method, especially with the advent of advanced technology such as adaptive optics and coronagraphs. These instruments work to reduce or block the star's overwhelming light, allowing telescopes to capture actual images of exoplanets or their immediate environments. Direct imaging is particularly effective for young, massive planets that emit heat as they cool down, often located at large orbital distances where the star's glare is less dominant. Such imagery not only confirms the planet's existence, but also allows study of its atmospheric properties and sometimes even weather patterns. Each method carries its unique strengths and limitations, often complementing one another. For example, a planet initially detected by radial velocity may later transit across its star from our vantage point, enabling a richer understanding through combined data. Similarly, microlensing can reveal planets in star systems that other methods cannot reach, painting a more comprehensive picture of planetary demographics across the galaxy. In recent years, astronomers have also begun examining variations and combinations of these techniques to detect smaller, Earth-sized planets and probe the atmospheres of these distant worlds with increasing precision. Innovations in spectrometry, high-contrast imaging, and space observatories dedicated to exoplanet research continue to push the boundaries of what can be observed and understood. Intimately linked with these detection methods is the profound patience inherent in the process. For instance, transit observations require monitoring a star over months or years to catch periodic dips in brightness, while radial velocity measurements necessitate precise, repeated observations over time to confirm a planet's influence on stellar motion. These patient, detailed studies have gradually unveiled a vast menagerie of worlds, from scorching hot Jupiters orbiting blisteringly close to their stars to warm super-Earths in potentially habitable zones, and exotic planets with bizarre compositions and orbits unlike anything in our solar system. Understanding how astronomers find hidden worlds deepens our appreciation of the discoveries themselves. These techniques embody the blend of human ingenuity and cutting-edge technology that has propelled us from vague speculation to detailed knowledge of planets light years away. The continuing refinement and diversification of detection methods promise a future rich with discovery, worlds yet unseen, atmospheres yet unprobed, potential hints of life waiting quietly in the cosmic night. As we prepare to delve next into the fascinating journey of the Kepler Space Telescope and its revolutionary contributions through transit detection, it becomes clear that the art of finding exoplanets is both a scientific achievement and a testament to humanity's enduring curiosity. The shadows that planets cast, the subtle wobbles they induce in their stars, and the fleeting gravitational alignments they orchestrate are all whispers from the cosmos, inviting us to explore the vast and varied family of worlds beyond our own. As we proceed deeper into the unfolding saga of exoplanet exploration, the story of the Kepler Space Telescope emerges as one of the most luminous chapters in humanity's quest to uncover distant worlds. The concept behind transits, the subtle, temporary dimming of a star's light caused by a planet crossing its face, provided a transformative method that dramatically accelerated the pace of discovery. Kepler was the first space observatory dedicated almost entirely to exploiting this method, and its success reshaped our understanding of how common planets are in the galaxy. Let us embark on a detailed journey to understand this ingenious method, the extraordinary technology behind Kepler, and how the telescope illuminated the night sky with revelations of thousands of hidden worlds. The transit method itself is elegantly simple in concept, yet profound in execution. Imagine staring up at a distant star, a blazing beacon of light in the dark cosmic sea. Occasionally, if a planet passes directly between that star and your vantage point, it blocks a tiny fraction of the star's light. Like a moth briefly fluttering across a lamp's distant glow. This results in a slight, predictable dip in brightness, often only about 1% or even less, but just enough to hint at the planet's presence. Detecting these subtle shadows requires extraordinary sensitivity and stability, something nearly impossible from the Earth's surface due to atmospheric turbulence and changing light conditions. This is where the brilliance of a dedicated space telescope like Kepler came into its own. Launched by NASA in March 2009, the Kepler Space Telescope was designed to continuously monitor the brightness of over 150,000 stars in a fixed patch of the Milky Way, located in the constellations Cygnus and Lyra. Its mission was to detect those infinitesimal declines in stellar brightness caused by transiting planets. Kepler's instrumentation was highly specialized. A 1.4-meter diameter photometer collected light, while its exquisitely sensitive charge-coupled devices, CCDs, recorded the brightness of stars with incredible precision and cadence. Unlike earlier detections relying on ground-based telescopes that could observe only during clear nights, Kepler orbited the Sun, outside Earth's shadow, enabling almost uninterrupted observation over years. This allowed astronomers to catch multiple transits of the same planet, confirming its existence and determining the planet's orbital period. One of the most profound contributions of Kepler was its ability to reveal not just large gas giants close to their stars, but also smaller Earth-sized planets orbiting within the so-called habitable zones, regions around stars where temperatures might allow for liquid water, a crucial ingredient for life as we know it. Prior to Kepler, it was unsure how common such worlds might be, or even if they existed. During its primary mission spanning from 2009 to 2013, Kepler discovered more than 2,600 confirmed exoplanets and yielded thousands of additional candidates awaiting verification. Its wealth of data not only expanded the catalog of known exoplanets exponentially, but also provided insights into the diversity of planetary sizes, orbits, and system architectures. From rocky worlds smaller than Earth to gigantic hot Jupiters and multi-planet systems packed tightly around their parent stars, Kepler unveiled a galaxy teeming with planetary complexity. Kepler's discoveries also revolutionized our understanding of planetary occurrence rates. By statistically analyzing the frequency and distribution of transiting planets among its monitored stars, astronomers concluded that planets are likely the rule rather than the exception in our galaxy. Estimates suggest that most stars harbor at least one planet, with many boasting multiple worlds in their gravitational embrace. But what truly makes the transit method and Kepler's mission so powerful is the depth of information encoded in those fleeting dips in starlight. The amount of light blocked tells us the planet's size. The timing between transits reveals the orbital period. When combined with radial velocity measurements, scientists can estimate a planet's density, yielding clues about its composition, whether a dense, rocky body or a gas-dominated giant. Moreover, in special cases, the spectral analysis of the starlight passing through a planet's atmosphere during transit, the so-called transmission spectroscopy, opens a window into alien atmospheres. This technique has detected atmospheric components such as hydrogen, sodium, and even water vapor on certain exoplanets, glimpsing worlds far beyond our solar system in startling detail. Kepler also encountered unexpected phenomena, from planets orbiting binary star systems, known as circumbinary planets, to compact planetary systems where many planets orbit closer to their star than Mercury does to our Sun. These discoveries challenged traditional models of planetary formation and stirred the imagination of both scientists and the public. Yet, the journey was not without challenges. After several years in space, Kepler's pointing precision was compromised by the failure of two reaction wheels, devices crucial for stabilizing the telescope's orientation. Ingeniously, NASA scientists reconfigured the mission into K2, repurposing the telescope to observe different fields of stars along the ecliptic plane, continuing to find planets, albeit at a different pace. The legacy of the Kepler mission extends far beyond its immediate discoveries. It fundamentally altered how astronomers approach planet finding, laying the groundwork for future missions like NASA's Transiting Exoplanet Survey Satellite, TESS, and the European Space Agency's Plato mission. These successors build on Kepler's pioneering techniques to survey brighter, closer stars and seek Earth-like worlds in our cosmic neighborhood. Kepler's success is a testament to the scientific ingenuity required to locate planets not directly visible, relying solely on the knowledge that even the smallest shadow can reveal a world. It transformed exoplanet research from a nascent field into a thriving branch of astronomy and triggered a profound shift in our cosmic perspective. We are not alone in hosting planets. Instead, the galaxy is abundant with worlds of every description. As we fold these reflections into our exploration, the tale of transits and shadows segues gracefully into the next methods of detection. We shall soon delve into radial velocity and the subtle stellar wobbles that complement transit observations. Together, these techniques weave a richer tapestry of discovery, each contributing vital pieces to the puzzle of our universe's planetary population. In the vast expanse of space, where distant stars glimmer like scattered diamonds on a velvet canvas, The quest to find planets beyond our solar system hinges upon subtle clues, almost imperceptible telltales wrought by gravity itself. Among the earliest and most successful methods for detecting exoplanets is the radial velocity technique, a fascinating approach that captures the delicate star dances choreographed by the gravitational pull of unseen orbiting worlds. This method, relying on precise measurement of starlight shifts through Doppler spectroscopy, has shaped our earliest exoplanet discoveries and continues to provide invaluable insights into alien planetary systems. To grasp the essence of the radial velocity method, envision a star and its planet locked in an intricate gravitational embrace. While we tend to picture the planet orbiting a relatively immobile star, in reality, both bodies revolve around a common center of mass, known as the barycenter. For massive stars and smaller planets like Earth, this wobble is minuscule, but for large, closely orbiting planets, the star's motion becomes discernible. This movement imparts a tiny oscillation in the star's velocity toward or away from Earth, detectable in the very light the star emits. The foundational principle behind radial velocity detection is the Doppler effect, a physical phenomenon familiar to us in everyday life. Just as the pitch of a passing ambulance siren rises as it approaches and falls as it recedes, the wavelength of light changes depending on whether the source moves toward or away from an observer. For a star, when moving slightly toward us, its spectral lines shift toward shorter, bluer wavelengths. Moving away, they shift toward longer, redder wavelengths. By analyzing these minuscule shifts, sometimes as tiny as a few meters per second, astronomers can infer the presence of an orbiting planet tugging on the star gravitationally. Implementing this technique requires the use of spectrographs of extraordinary precision. These instruments disperse a star's light into its constituent colors, producing a spectrum marked by characteristic absorption lines created by elements in the star's atmosphere. The critical task is to detect and measure the shifts in these spectral lines over time, signifying changes in stellar velocity. Early instruments achieved remarkable precision, but advances in technology, such as stabilized spectrographs employing laser frequency combs and ultra-stable calibration sources, have pushed sensitivities to velocities of mere centimeters per second, edging closer to the detection of Earth-like planets. The breakthrough discovery, made using the radial velocity method, arrived in 1995 with the detection of 51 Pegasi b, a hot Jupiter closely orbiting its star. By observing the wobbles of 51 Pegasi's spectrum, Michel Mayor and Didier Queloz demonstrated how the technique provided an indirect yet reliable signature of an exoplanet's presence. This monumental success ushered in a new era in astronomy and spurred development of ever more sensitive instruments worldwide. One of the assets of radial velocity measurements is the wealth of information they yield. Beyond mere detection, careful measurement of the amplitude and period of the stellar wobble enables astronomers to calculate the planet's minimum mass, the least mass it must have to cause the observed effect, and its orbital period. Determining the orbital period reveals the distance from the star through Kepler's laws of planetary motion, while the mass suggests the planet's possible nature, whether rocky, gaseous, or somewhere in between. However, the method has limitations. Because radial velocity only reveals the wobble component along our line of sight, it cannot by itself provide the planet's exact mass, but rather a minimum mass, unless complemented by additional observations from other methods such as transits. Additionally, the method favors detection of massive planets close to their stars, where the gravitational pull is greatest, making it challenging to discern the subtle wobbles induced by smaller, Earth-sized planets in wider orbits. Contemporary facilities have refined radial velocity surveys further, using dedicated instruments mounted on giant ground-based telescopes such as the high-accuracy radial velocity planet searcher, HARPS, in Chile, and ESPRESSO on the Very Large Telescope. These spectrographs have expanded the frontier, enabling detections of smaller planets in closer proximity to their stars, widening the scope of exoplanet demographics. The radial velocity method not only aids in discovering planets, but also benefits from synergy with other detection techniques. When a planet is identified transiting its host star, radial velocity measurements can be used to determine the planet's mass, allowing the calculation of the planet's density, a vital clue to its internal composition. Such multi-method confirmation has turned into a standard practice in confirming exoplanet candidates and characterizing their properties. Furthermore, radial velocity surveys have unraveled the rich variety of planetary system architectures. They have uncovered not just solitary planets, but multi-planet systems, some with planets in orbital resonances, others with eccentric orbits. The method has revealed exoplanets around a broad range of stellar types, from sun-like stars to red dwarfs, and even giant stars nearing the ends of their lives, providing valuable data points on how planetary formation evolves with time and stellar environment. Beyond refining science, radial velocity also faces profound challenges. Stellar activity, such as star spots, flares, and oscillations, can mimic or mask the signals caused by orbiting planets, requiring astronomers to carefully disentangle planetary wobbles from stellar noise. Addressing these challenges involves sophisticated statistical techniques and extended monitoring to distinguish true planetary signals. This delicate interplay between gravitational forces, light, and complex stellar phenomena illustrates the ingenuity required in the hunt for distant worlds. Radial velocity brings into focus the invisible gravitational dance, an elegant cosmic whisper that guides us to worlds we cannot see directly, but can understand through their subtle influences. As we continue to refine this method alongside others, the combined methodologies enhance our capacity to catalog and characterize an ever-widening array of exoplanets. The radial velocity technique, with its profound ability to detect masses and orbits, remains complementary to photometric transit observations, microlensing events, and direct imaging efforts. The next chapter in our exploration will guide us into the realm of microlensing and direct imaging techniques that unlock access to worlds concealed even from the powerful grasp of radial velocity and transit detection. These methods push the boundaries further out, unveiling exoplanets by their gravitational mirages and by capturing direct photons of alien worlds themselves, broadening the vista of exoplanet discovery and understanding on the grand scale of the cosmos. In the grand pursuit of uncovering planets beyond our solar system, astronomers have harnessed a variety of innovative techniques, each unveiling hidden worlds through different cosmic clues. After exploring the transit and radial velocity methods, we now turn to two other methods that, while less heralded in popular discussions, hold remarkable power in reaching into the farthest and most elusive corners of our galaxy: microlensing and direct imaging. These two approaches extend our gaze to worlds that evade other detection methods, offering unique insights into planetary populations and shining a light, quite literally, on planets orbiting stars too faint, distant, or complex for other techniques to untangle. Beginning with microlensing, this method is grounded in one of the most elegant phenomena predicted by Einstein's general theory of relativity: gravitational lensing. When a massive object, such as a star with its own planetary entourage, passes nearly in front of a more distant background star as viewed from Earth, its gravity warps space-time enough to act like a lens. This cosmic lens bends and magnifies the light of the background star, momentarily brightening it in a signature pattern known as a microlensing event. This natural magnifying effect is subtle and rare, requiring precise alignment between the observer, the lensing star, and the distant light source. When planets accompany the lensing star, they introduce additional small but distinct blips in the magnification curve, betraying their presence despite their faintness and the vast distances involved. Often thousands of light-years away, in parts of the galaxy poorly accessible to other methods. Because microlensing does not rely on the planet's light or direct interaction with its star's emission, it is especially adept at detecting planets around faint stars or even free-floating rogue planets wandering the galaxy without a star. The power of microlensing lies in its ability to find planets in a broad range of masses and orbital distances, including those on wide orbits comparable to or exceeding Earth's distance from the Sun. For instance, microlensing surveys have discovered cold, low-mass planets orbiting far from their host stars, regions largely invisible to transit searches or radial velocity surveys. By piecing together data from hundreds of microlensing events detected by ground-based collaborations such as the Optical Gravitational Lensing Experiment, OGLE, and the microlensing observations in astrophysics, EMOI, astronomers have begun assessing the prevalence and distribution of planets throughout the galaxy's dense stellar fields. Yet, microlensing's strength comes with challenges. Its events are unpredictable, transient, and typically one-time occurrences. Once a microlensing event passes, it cannot be reobserved. This ephemerality demands continuous, high-cadence monitoring of vast star fields to catch these fleeting gravitational alignments. Moreover, because radial velocity and transit conformations are generally impossible for microlensing detections, given the great distances and faintness of targets, astronomers rely on meticulous modeling of light curves and statistical analyses to characterize newly found planets. In a different but equally captivating approach, direct imaging offers the singular thrill of capturing photons reflected or emitted directly from an exoplanet itself, enabling the extraction of details about the planet's atmosphere, temperature, and even weather patterns. Achieving this feat is a spectacular technical challenge, as planets are vastly dimmer than their host stars, often 1/1000th the brightness or less, and typically separated by distances so minuscule from our vantage point that they are nearly lost in the stellar glare. Astronomers overcome these hurdles by combining cutting-edge technologies and observing strategies. Adaptive optics systems counteract the blurring effects of Earth's atmosphere, sharpening stellar images to near their theoretical limit. Coronagraphs are specialized instruments designed to block or suppress the light from a star, creating an artificial eclipse within a telescope's view and revealing faint nearby companions. Direct imaging is especially effective for young, massive, and hot planets that still radiate residual heat from their formation, primarily located at relatively large orbital distances from their stars, tens to hundreds of astronomical units, the average distance between Earth and the Sun. These planets shine with infrared light, which ground-based observatories equipped with advanced infrared detectors can capture. Early direct imaging discoveries, such as those of the HR 8799 system's multiple massive planets or the famed Beta Pictoris b, have provided stunning visual confirmation of planetary companions and paved the way for in-depth atmospheric characterization. Space telescopes also play a vital role. The Hubble Space Telescope and, more recently, the James Webb Space Telescope have contributed to direct imaging studies, offering stable, high-contrast observations free from atmospheric disturbances. Moreover, upcoming missions like NASA's Nancy Grace Roman Space Telescope promise to revolutionize direct imaging with planned instruments specifically designed to detect and study exoplanets using advanced coronagraphs. While still limited in the range of planets they can detect compared to transit or radial velocity surveys, direct imaging remains a cornerstone for understanding planet formation and evolution. By examining the light emitted or reflected by the planet itself, scientists can deduce atmospheric molecules such as water vapor, methane, or clouds, assess thermal properties, and witness dynamic weather phenomena. These observations provide invaluable ground truth to theoretical models. When considered together, microlensing and direct imaging complement each other and the other planet detection methods, expanding the volume and diversity of planets accessible to astronomy. Microlensing peeks into the galaxy's crowded and distant stellar neighborhoods, revealing populations of planets beyond the immediate solar vicinity, while direct imaging allows us to study planetary environments and processes firsthand. These methods enrich our cosmic narrative by uncovering classes of planets and planetary systems that challenge traditional ideas and deepen our understanding of the myriad possibilities for planet formation throughout the Milky Way. From wandering rogue planets unbound by any star to young giants glowing in infrared embers, microlensing and direct imaging broaden the tapestry of worlds that inspire dreams and scientific curiosity alike. As we step onward in our exploration, the next chapters will ponder what renders some exoplanets truly mysterious, from their enigmatic features to the criteria by which astronomers classify the vast diversity of these alien worlds. The techniques and discoveries we've just explored lay the groundwork for deciphering the secrets hidden within these mysterious realms, as our journey into the galaxy's strange and wonderful exoplanetary menagerie continues. As we move into the realm of exoplanets that capture both scientific intrigue and the imagination, we inevitably encounter worlds termed mysterious. Planets whose characteristics defy easy explanation, challenge existing models, or evoke questions almost poetic in their ambiguity. But what exactly makes an exoplanet mysterious? Is it the peculiarity of its orbit, its composition, or the hints it offers about the unknown? This chapter seeks to define the criteria and categories through which astronomers classify certain exoplanets as mysterious, revealing how complexity and enigma fuel the ongoing quest for understanding. The first point to recognize is that the term mysterious is not strictly scientific, but blends observational criteria with the frontiers of our current knowledge. As we categorize exoplanets, several overlapping attributes contribute to their mysterious classification. One primary criterion is deviation from expected planetary types or models. Since the first discoveries, planetary formation theories predicted certain outcomes. Gas giants should form in the colder, outer regions of a system. Smaller rocky worlds should be closer in. Planetary orbits tend to be roughly circular and coplanar. Yet many exoplanets defied these assumptions. Hot Jupiters, massive gas giants scorching in orbits closer than Mercury to their stars, challenged formation models, raising questions about planetary migration and the dynamic histories of systems. Planets with highly elliptical orbits, wildly inclined orbital planes, or those orbiting unusual hosts such as pulsars or binary stars also fall into the mysterious category because they stretch the boundaries of normative theory. Secondly, atmospheric composition serves as a crucial lens into a planet's nature, and the detection of unusual or unexpected atmospheric signatures adds a layer of mystery. For example, observations revealing clouds of vaporized metals or atmospheric molecules present in ratios defying chemical equilibrium force scientists to rethink prevailing atmospheric models. The presence of unusual chemical fingerprints, such as excessive carbon compounds or hazes that obscure analyses, suggests processes not yet fully understood and often points to exotic weather and climate phenomena. These atmospheric oddities intrigue researchers, prompting deeper observation and theoretical exploration. Size and density anomalies also enter into this arena. Planets with extraordinarily low densities, sometimes called puffy planets, appear as comically inflated worlds, vastly larger than expected for their masses, suggesting atmospheres bloated by intense radiation or internal heat. Conversely, planets with masses seemingly too large for their observed sizes challenge interior composition theories, perhaps hinting at exotic core materials or unexpected compressive forces. Such worlds raise questions about their formation, structure, and evolution, casting them into the mysterious realm. Another noteworthy category involves exoplanets exhibiting unusual light curves or variability. For instance, some stars show irregular dips in brightness that do not match the simple, regular profiles expected from planetary transits, implying complex circumstellar environments such as debris disks, ring systems, or planetary fragments. Also, intermittent or fluctuating signals might hint at dynamic atmospheres or interacting planets, all phenomena that defy straightforward interpretation and demand nuanced study. Orbital dynamics also contribute to mysteries. Rogue planets wandering interstellar space without a star challenge planetary classification itself. Their origins, whether ejected from star systems or formed in isolation, remain topics of debate. Planets in compact multi-planet systems with resonant orbits, or those orbiting extremely faint or active stars, raise additional puzzles about stability and habitability. In the broader observational context, mysterious exoplanets often arise when data is limited or ambiguous, necessitating careful interpretation among multiple competing hypotheses. These edge cases are both the scientific frontier and the source of profound wonder. The most perplexing exoplanets invite interdisciplinary approaches, combining astrophysics, planetary science, atmospheric chemistry, and even astrobiology to unlock their secrets. Examples abound. Planets like WASP-12b, one of the darkest known planets, absorb almost all light without reflecting it, puzzling scientists about its atmospheric composition and cloud dynamics. Others, like HD 189733b, display violent weather systems with blazing winds and exotic precipitation, such as raining glass. The enigmatic variability observed in stars like Kiku 84628552, known as Tabby's star, has generated theories ranging from swarms of comets to hypothetical alien megastructures, illustrating how mysteries can spur diverse lines of inquiry. To organize these diverse phenomena, astronomers categorize mysterious exoplanets into groups based on the dominant features confounding explanation: anomalous orbits, aberrant physical characteristics, unusual atmospheric chemistry, and unexplained photometric behavior. These groupings help focus investigation and foster theoretical advances. The study of such peculiar worlds is more than academic curiosity. It challenges our assumptions about how planets form and evolve, and by extension, how unique or common conditions conducive to life might be. Each mysterious exoplanet serves as a cosmic riddle, inviting us to reconsider the architectures of planetary systems and the chemical pathways that generate diverse planetary environments. Importantly, the label mysterious also underscores the dynamic nature of science itself. What is mysterious today may become well understood tomorrow as new techniques, instruments, and theories emerge. The pursuit of these enigmas drives technological innovation and cross-disciplinary collaboration, fueling the steady march toward profound cosmic insights. Moreover, the fascination with mysterious exoplanets impacts cultural perspectives, inspiring art, literature, and philosophical reflection on our place in the universe. Their mysteries remind us of the vastness of what remains unknown, inviting humility and curiosity as we gaze into the depths of space. In the chapters to come, we will journey through some of the most astonishing categories of exoplanets, exploring the fiery hot Jupiters, dense super-Earths, and enigmatic Mini-Neptunes that embody the diversity of our galactic neighborhood. Each serves as a testament to the endless variety and complexity thriving in the cosmic wilderness, elevating our fascination with the mysterious beyond the reaches of our home star system. Venturing further into the cosmos, we find ourselves amidst a veritable menagerie of alien worlds, planets that defy the neat categories of our own solar system, revealing a staggering diversity that stretches the imagination and challenges our theories of planetary formation and evolution. Among the myriad types discovered, 3 categories have emerged as particularly fascinating due to their contrasting characteristics and the unique insights they offer: hot Jupiters, super-Earths, and mini-Neptunes. Each category embodies a fragment of the vast tapestry of planetary diversity, demonstrating the remarkable range of sizes, compositions, and orbital configurations that exist beyond our solar neighborhood. Let us begin with the hot Jupiters, a class of gas giants that boldly defy early assumptions about where giant planets can exist. These worlds are titans by scale, often several times the mass of Jupiter, the giant king of our solar system. But their defining feature is their blisteringly close orbit to their stars, sometimes completing a revolution in just a few days. This proximity subjects them to extreme stellar radiation and tidal forces, scorching their atmospheres and inflating their sizes beyond what would normally be expected. Hot Jupiters are thought to have formed further from their stars, in the colder outer regions of their planetary systems, accruing massive envelopes of hydrogen and helium gas. Through processes yet not fully understood, these giants then migrated inward, forging orbits so tight that any life as we know it is virtually impossible. The existence of hot Jupiters was one of the first major surprises in exoplanetary science. It upended traditional models that predicted gas giants should remain in the colder, outer reaches, like Jupiter and Saturn in our own solar system. Studying hot Jupiters provides clues about planetary migration mechanisms and atmospheric physics under extreme conditions. Their inflated atmospheres, intense stellar winds, and sometimes complex weather systems offer laboratories for understanding gas giant behavior outside the solar system context. Notable examples such as 51 Pegasi b and WASP 12b have been extensively observed, revealing phenomena like tidal distortion, atmospheric escape, and intense thermal radiation. Next, turning our gaze to super-Earths, a fascinating category that resides in a size regime absent from our solar system. These are planets larger than Earth, but substantially smaller than the ice giants Uranus and Neptune. Typically ranging up to about 10 times Earth's mass and up to twice its radius, super-Earths offer a tantalizing glimpse at worlds that may bridge the gap between rocky planets like our own and gas-dominated giants. The true nature of super-Earths is still a subject of intense research and debate. Some may be predominantly rocky, possessing thick atmospheres rich in nitrogen, carbon dioxide, or water vapor. Others may have substantial layers of volatiles or ices, blurring the lines between rocky and gaseous compositions. Their relatively high densities in some cases suggest rocky interiors, while lower densities imply thick gaseous envelopes. This variability makes them a critical focus for understanding planetary formation and habitability. Super-Earths often orbit close to their stars, sometimes within the habitable zone, opening the exciting possibility that some may possess conditions suitable for liquid water and perhaps life. However, factors like stellar radiation, atmospheric retention, and geological activity complicate this picture. Missions such as Kepler and TESS have revealed an abundance of super-Earths, hinting that they might be among the most common types of planets in the galaxy. Mini-Neptunes, closely related but distinct from super-Earths, are smaller than Neptune but larger than Earth. often with thick hydrogen and helium atmospheres that envelop denser cores. These worlds tend to have lower densities than super-Earths, reflecting their substantial gaseous envelopes. They often form in regions where accumulating gas from the protoplanetary disk was sufficient to create extended atmospheres, but not enough to trigger runaway gas accretion like Jupiter. The distinction between mini-Neptunes and super-Earths is sometimes blurred, with transitional classes existing. But in general, mini-Neptunes represent a category of volatile-rich planets with potentially profound differences in climate, surface conditions, and atmospheric chemistry. These distinctions challenge our ability to classify exoplanets based solely on size and mass, underscoring the importance of detailed atmospheric and orbital data. Understanding these classes extends beyond mere categorization. Hot Jupiters, super-Earths, and mini-Neptunes exemplify the incredible diversity in planetary formation outcomes, influenced by factors such as the protoplanetary disk's composition, stellar radiation, planetary migration, and system dynamics. Each class raises profound questions. How common are these types throughout the galaxy? What do their characteristics tell us about the evolution of planetary systems? Could some among them be habitable, or at least possess environments that challenge our Earth-centric notions? Our exploration of these diverse alien worlds sets the stage for investigating how we might narrow the search for habitable conditions, a journey that will introduce us to the concept of the Goldilocks Zone, where planets neither scorch in the fires of their stars nor freeze in the cosmic cold. But before venturing there, let us continue to reflect on the remarkable breadth of planetary diversity that defines the galaxy's architectural grandeur, a reminder of nature's propensity for endless variation and wonder. Among the vast and varied exoplanets discovered beyond our solar system, one concept has captured the collective imagination of scientists and the public alike: the Goldilocks Zone. This evocative term refers to the narrow orbital region around a star where conditions might be just right, not too hot, not too cold, for liquid water to exist on a planet's surface. Since water is widely regarded as essential for life as we know it, the Goldilocks Zone represents a promising criterion in the search for habitable worlds. Yet, while the idea sounds simple, the reality of locating truly habitable exoplanets within this zone is complex, nuanced, and deeply fascinating. To understand the Goldilocks Zone, we first consider the role of a star's energy output. A planet that orbits too close to its star will endure searing temperatures, likely causing any surface water to evaporate and escape into space. Conversely, a planet too distant from its star will be locked in freezing conditions where water solidifies as ice, hampering the chemical processes believed necessary for life. The Goldilocks Zone, the habitable zone, is the range in between where an orbiting body could maintain stable liquid water, assuming an atmosphere with sufficient pressure and composition. However, the boundaries of this zone are not fixed. They vary depending on the type, size, and temperature of the host star. Smaller, cooler stars, such as red dwarfs, have habitable zones that lie much closer in, whereas larger, hotter stars possess wider, more distant habitable zones. Moreover, stellar variability and evolution can shift these zones over time, altering a planet's potential for habitability across geological timescales. One of the key insights brought by the study of exoplanets is the realization that being in the Goldilocks Zone alone does not guarantee habitability. A planet's atmosphere, the thickness, composition, and greenhouse gas content, plays a critical role in regulating surface temperatures and maintaining liquid water. For example, a planet with a thick carbon dioxide-rich atmosphere may retain heat more efficiently and be habitable even on the colder edge of the zone, while a planet lacking an atmosphere might remain barren and lifeless despite orbiting squarely within the zone. Tidal locking adds another layer of complexity. Planets orbiting close to small stars often become tidally locked, where one hemisphere is perpetually facing the star while the other remains in darkness. This creates extreme temperature gradients that could challenge atmospheric circulation and the retention of surface liquid water, although some models suggest that atmospheres or oceans could moderate these disparities, preserving habitability. Exoplanet missions, such as NASA's Kepler and the Transiting Exoplanet Survey Satellite, TESS, have dramatically expanded the catalog of planets within habitable zones, igniting excitement about potential Earth analogs. Notable discoveries like Kepler 100EF and Kepler 452b reside within the habitable zones of their stars and stimulate hope for finding worlds with conditions conducive to life. Yet much remains unknown. Details about their atmospheres, geologies, and histories are still elusive. Beyond the classical definition, recent research considers additional factors influencing habitability. Geophysical activity, such as volcanism and plate tectonics, may sustain atmospheres and recycle essential nutrients. Magnetic fields can shield atmospheres from stellar winds and cosmic radiation, preserving habitable conditions. The presence of moons can also impact planetary climates and stability. The search for habitable conditions also encompasses the broader concept of the circumstellar habitable zone, which extends to consider subsurface environments, such as oceans beneath icy crusts, shielded from harsh surface conditions. This extends the possibilities for life beyond the traditional Goldilocks boundaries. Ultimately, the Goldilocks Zone is a vital starting point, a guiding beacon in the vast sea of exoplanetary data. It focuses our gaze on worlds where the delicate balance of physics and chemistry might foster life, propelling targeted observation and study. With next-generation telescopes like the James Webb Space Telescope and upcoming missions on the horizon, astronomers are poised to peer into these habitable zones, probing planetary atmospheres for signs of water, oxygen, and biosignatures. As we continue, we will uncover yet more fascinating cases of planets in exotic, sometimes eccentric orbits. Worlds that wander alone, or follow elliptical paths that challenge the simplicity of the habitable zone concept. These weird and wonderful orbits compel us to deepen our understanding of habitability's many nuances, as our journey to comprehend life's potential beyond Earth unfolds across the universe. As we journey deeper into the cosmos and uncover the diverse family of exoplanets, we find that not all planetary orbits fit the neat, circular paths familiar from our solar system. Instead, a menagerie of strange and captivating orbital configurations emerge, orbits that twist, wander, and defy expectations. Among these, two particularly astonishing phenomena stand out: rogue planets that drift through interstellar space unaffiliated with any star, and planets tracing wildly elliptical, sometimes chaotic, pathways around their suns. These weird and wonderful orbits not only challenge our traditional notions of planetary systems, but also offer profound insight into the dynamic and sometimes violent processes that shape planetary evolution. First, consider rogue planets, also known as free-floating planets. Unlike the planets orbiting familiar stars, rogue planets wander the darkness of interstellar space, unbound from any parent star's gravity. These cosmic nomads might have formed in planetary systems only to be ejected by gravitational interactions with other massive bodies. Or alternatively, they might have formed independently, akin to stars, but lacking the necessary mass to initiate fusion. Their existence was long hypothesized, but only in recent decades have technology and observation techniques hinted at their presence. Detecting rogue planets is challenging because, without a nearby star to illuminate them, they are faint and cold. astronomers often rely on gravitational microlensing, the gravitational bending and magnification of light from a background star as the rogue planet passes near the line of sight to infer their presence. Surveys such as the Optical Gravitational Lensing Experiment, OGLE, have identified candidate rogue planets, suggesting there may be billions of these nomads in our galaxy alone. The implications of rogue planets roaming the galactic void are profound. These wanderers might harbor subsurface oceans insulated by thick ice layers, potentially heated by internal radioactive decay or residual heat from formation, thus providing intriguing prospects for exotic, isolated habitats. Their very existence forces astronomers to reconsider the stability and long-term dynamics of planetary systems, the mechanisms by which planets can be gravitationally ejected, altering the architecture of star systems dramatically. Turning to elongated and eccentric orbits, many exoplanets defy the predominantly circular orbits of the solar system's planets. Some boast elliptical orbits that bring them scorching close to their star at perihelion and then cast them into frigid darkness at aphelion. These variations in distance lead to extreme seasonal changes, wildly fluctuating surface temperatures, and atmospheric conditions that challenge models based largely on Earth's relatively stable orbit. The causes of such eccentric orbits often lie in the turbulent birth and evolution of planetary systems. Interactions with sibling planets, nearby stars, or remnants of planetary formation can perturb orbits, sometimes leading to dramatic gravitational reshaping. Additionally, migratory processes, resonances, or even passes through debris disks can pump up orbital eccentricity. These elliptical trajectories offer astronomers natural laboratories for testing theories of planetary climate and geology under extreme and variable conditions. For hypothetical life forms, such environments would demand adaptability to temperature swings and radiation fluctuations far removed from Earth's habitability norms. Another intriguing class comprises planets locked in orbital resonances, where their orbits are synchronized in harmonic ratios with one or more companion planets. These gravitational dances can stabilize or destabilize systems, influence orbital eccentricities, and affect conditions on the planets themselves, creating intricate celestial choreography. Furthermore, some planets orbit binary star systems, known as circumbinary planets, tracing orbits around two suns. This configuration introduces complex gravitational dynamics, shaping orbital paths in ways distinct from planets orbiting single stars. The famous Kepler-16b, affectionately dubbed a Tatooine planet for its double sunset, exemplifies these fascinating systems. Collectively, the weird and wonderful orbits embraced by rogue planets, eccentric trajectories, resonant dances, and binary star companions illustrate the incredible dynamism of planetary systems. They remind us that our solar system's relative calm and order might be a rarity rather than the norm. Studying these peculiar orbits reveals the sometimes violent and chaotic processes underpinning planetary formation and evolution. They show us that planets can be cast adrift, locked in celestial rhythm, or wildly swung by gravitational tides, each journey shaping worlds in unpredictable ways. As we continue our voyage into the exoplanet realm, these fascinating orbital phenomena prepare us to better understand mysterious atmospheric traits, tidal locking effects, and even the potential for life in environments radically unlike our own. The dance of planets, sometimes harmonious, sometimes frenzied, is a cosmic story of motion, change, and enduring wonder. As humanity's gaze extends ever outward into the cosmic ocean, a new frontier unfolds. Not just finding the planets themselves, but peering deep into their atmospheres, into the very skies of these distant worlds. Atmospheric studies of exoplanets promise to transform the abstract dots of light into dynamic, complex worlds, revealing climates, chemistry, and perhaps even hints of life. This grand endeavor, once a distant dream, is now rapidly becoming reality through the power of next-generation telescopes and ingenious observational techniques. In this chapter, we explore the atmospheric mysteries that exoplanets present and how cutting-edge instruments unravel the complex tapestries woven into alien skies. Exoplanet atmospheres are veils that cloak these distant spheres, composed of gases whose composition and dynamics can reveal much about a planet's nature, history, and potential habitability. The atmosphere influences surface conditions, protects from stellar radiation, and drives weather patterns. Yet, studying these ethereal layers light-years away is an extraordinary challenge. The planets are faint, often lost in the overwhelming glare of their host stars, and atmospheric signals are subtle fingerprints within that faint light. One of the seminal methods employed to study exoplanet atmospheres is transmission spectroscopy. This technique analyzes the starlight that filters through a planet's atmosphere during a transit, when the planet crosses its star from our perspective. Molecules and atoms in the atmosphere absorb specific wavelengths of light, imprinting characteristic absorption lines onto the observed spectrum. By comparing spectra obtained during transit to those taken when the planet is elsewhere in its orbit, scientists can identify the atmospheric constituents: water vapor, methane, carbon dioxide, sodium, and more. Early successes in atmospheric characterization came from the Hubble Space Telescope, which detected signatures such as sodium in the atmosphere of HD 22945, 8b, a hot Jupiter. This initial breakthrough illuminated the path forward, prompting the development and launch of telescopes optimized for atmospheric study. Enter the James Webb Space Telescope, JWST, a transformative instrument providing unparalleled sensitivity and spectral resolution in the infrared. Since its deployment, JWST has embarked on ambitious exoplanet observations capable of probing smaller, cooler worlds than previously possible. Its advanced spectrometers can detect faint molecular fingerprints, even in tenuous atmospheres, and measure thermal emission from planets, revealing temperature structures and weather systems. JWST's capabilities allow atmospheric scientists to examine clouds, hazes, and photochemical processes shaping alien skies. The detection of water vapor, a key molecule for life, is now routine for many hot exoplanets. More challenging, yet equally tantalizing, is the search for biosignature gases, molecules such as oxygen, ozone, or methane in specific combinations that might indicate biological activity. Ground-based observatories continue to play a vital role, equipped with instruments employing adaptive optics and high-dispersion spectroscopy. Telescopes such as the European Southern Observatory's Very Large Telescope and upcoming giants like the Extremely Large Telescope utilize advanced techniques to separate planetary light from the star, enabling direct spectral studies of atmospheric components. Another promising atmospheric probe is emission and phase curve spectroscopy. As a planet orbits its star, the observed brightness changes due to its phase, the varying fraction of the illuminated hemisphere visible to us. By measuring these changes at multiple wavelengths, scientists glean thermal maps, uncover hotspot shifts driven by winds, and explore atmospheric circulation patterns. These studies have revealed alien worlds with astonishingly dynamic atmospheres, titanic storms with winds howling at thousands of kilometers per hour, clouds of exotic compounds such as titanium oxide or corundum dust, atmospheres gradually evaporating under intense stellar exposure. Some planets exhibit mysterious features, including spectral signatures that defy current models, hinting at unknown chemistry or novel physical processes. Beyond single planets, comparative atmospheric studies across diverse exoplanet populations are revealing trends and patterns, how atmospheric composition varies with planet size, temperature, or stellar environment. Observations indicate that smaller planets may have lost thick hydrogen envelopes, revealing secondary atmospheres rich in heavier molecules, or that intense radiation shapes distinct atmospheric escape profiles. Looking ahead, upcoming missions such as the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, ARIEL, will provide comprehensive surveys of exoplanet atmospheres across the galaxy, vastly expanding the sample size and enabling more statistical understanding. These spacecraft will explore atmospheric diversity on a scale never before possible. The atmospheric mysteries of exoplanets are profound, bridging astronomy, chemistry, planetary science, and astrobiology. Each observation peels back a layer of these distant skies, transforming points of light into worlds with weather, climates, and chemical dramas. It is a pursuit that stretches human ingenuity and technology to the limits, and yet it is this detailed study of alien atmospheres that holds the promise of detecting the subtle signs that might hint at life beyond Earth. As our instruments sharpen and our understanding deepens, we stand on the cusp of a golden age in exoplanetary science, one that may reveal the secrets of distant skies and invite us to imagine the rich, diverse environments thriving in the cosmic night. From probing the searing gas giants to temperate rocky worlds, the mysteries of these alien atmospheres beckon as portals to new knowledge and profound discovery. Among the myriad exoplanets discovered in recent decades, some stand out not only for their peculiar characteristics, but also for the wealth of information they provide about planetary physics, atmospheres, and star-planet interactions. One such fascinating world is WASP-12b, often dubbed the blackest planet for its extraordinary ability to absorb nearly all the light that reaches it. This case study takes us on a journey to understand WASP-12b's remarkable properties, the methods used to uncover them, and what this enigmatic world teaches us about the diversity and complexity of alien planets. WASP-12b lies approximately 600 light-years from Earth in the constellation Auriga. Discovered in 2008 by the Wide-Angle Search for Planets (WASP) project, this exoplanet rapidly attracted scientific interest due to its extreme characteristics. It is classified as a hot Jupiter, a class of gas giants that orbit very close to their host stars. But WASP-12b pushes this class to astonishing extremes, orbiting its star at a distance of only about 0.00229 astronomical units, AU, less than 1/20th the distance from Earth to the Sun. WASP-12b completes a full orbit in a mere 1.009 Earth days. This incredibly tight orbit subjects it to intense stellar radiation and gravitational forces, leading to extreme surface and atmospheric conditions. Its dayside temperature soars to roughly 2,500 Kelvin, about 2,200 degrees Celsius, making it one of the hottest exoplanets known. Yet, what truly distinguishes WASP-12b is its exceptional darkness. Observations using space telescopes like Hubble and Spitzer revealed that the planet reflects less than 6% of the light that falls onto it, rendering it darker than charcoal or even fresh asphalt. This extraordinary absorption is thought to result from a combination of factors in its atmosphere, including thick layers of absorbing gases and a lack of reflective clouds, making it effectively a near-perfect black body absorber. Atmospheric studies suggest that WASP-12b hosts a peculiar chemical composition. High concentrations of carbon-rich molecules like methane and carbon monoxide dominate, while water vapor seems less abundant than expected. This carbon-rich atmosphere challenges traditional models of planetary atmospheres, which assume oxygen-rich compositions like those of Jupiter or Neptune. Theoretical work proposes that carbon-rich environments might promote exotic cloud particles made of materials such as graphite or silicon carbide, contributing further to the planet's absorptive properties. WASP-12b also exemplifies the brutal gravitational dynamics at play in ultra-close orbits. Tidal forces from the host star distort the planet, elongating its shape into a teardrop rather than a sphere, and likely stripping away its atmosphere. Estimates indicate that atmospheric material is escaping at enormous rates, creating a comet-like tail many times larger than the planet itself. This mass loss may ultimately lead to the planet's evaporation over astronomically short timescales. The host star itself responds to these interactions, showing signs of tidal heating and enhanced stellar activity, providing a natural laboratory for studying star-planet coupling mechanisms. Researchers continue to monitor WASP-12b's orbit and atmospheric composition to understand how such close-in giants evolve and interact dynamically with their stars. WASP-12b's extreme conditions have made it a focal point for both atmospheric modeling and observational campaigns. By capturing the spectrum of light emitted and absorbed by the planet, astronomers refine their understanding of heat redistribution in highly irradiated atmospheres. Questions about how energy is transported from the blazing day side to the cooler night side, how clouds form under such conditions, and what photochemical processes occur all find vivid expression in this planet. In a broader context, WASP-12b challenges preconceived notions about gas giants and the limits of planetary survivability. Its study pushes the boundaries of atmospheric science, planetary evolution, and the influence of stellar environments, enriching our understanding of the diverse planetary population. By examining the blackness and brutality of WASP-12b, we glimpse a world radically different from our own. Scorching, suffused in exotic chemistry, and caught in a death spiral of atmospheric escape, its story exemplifies the surprises lurking in the exoplanet catalog, where each discovery is a gateway to new questions and insights. As we transition from this molten giant, our next journey will take us to Kepler-22b, a planet bearing the promise of Earth-like conditions and rekindling hopes for finding truly habitable worlds beyond our cosmic doorstep. As our exploration of distant worlds deepens, among the countless discoveries shining like gems in the cosmic sea, few have stirred as much hope and wonder as Kepler-22b. This extraordinary exoplanet, unveiled by NASA's Kepler Space Telescope in 2011, emerged as one of the earliest promising candidates resembling our own Earth, not just in size, but in the tantalizing possibility of nurturing life. Kepler-22b's story offers a fascinating glimpse into the promise and challenges of finding truly Earth-like worlds beyond the solar system, igniting a renewed quest to answer the enduring question: are we alone? Kepler-22b orbits a Sun-like star approximately 600 light-years away in the constellation Cygnus. What immediately set Kepler-22b apart was its location within the star's habitable, or Goldilocks Zone. This orbital region promises conditions neither too hot nor too cold for liquid water to exist on the planet's surface, a fundamental prerequisite for life as we understand it. Completing an orbit every 289 days, remarkably close to Earth's 365-day year, Kepler-22b dwells at a comfortable distance akin to Earth's place around the Sun. The planet measures roughly 2.4 times Earth's radius, positioning it between a super-Earth and a mini-Neptune in terms of size. Although more substantial than Earth, this size makes it one of the best candidates known at the time for possessing a solid surface, though its exact composition remains uncertain. Importantly, Its density and atmospheric nature have yet to be directly measured, leaving open questions about its true character, whether rocky, oceanic, or covered by a thick gaseous envelope. Kepler-22b's discovery was groundbreaking, not merely as a dot in distant space, but as a proof of concept that terrestrial-sized planets reside in habitable zones, rekindling optimism about finding life-friendly environments. Its relatively stable star, with similar spectral characteristics and age to our Sun, enhances its allure. The concept of a planet comfortably circling a familiar star, potentially with temperate climates, resonates deeply with the imagination. Studying Kepler-22b involves analyzing subtle light dips as it transits its star, allowing astronomers to infer its size and orbit, but the limitations imposed by distance and current technology constrain direct study of its atmosphere and surface. Yet, advances in observational techniques and forthcoming space telescopes, such as the James Webb Space Telescope, aim to peel back these layers of mystery, enabling examination of atmospheric components, thermal profiles, and perhaps biomarkers. Kepler-22b challenges and enriches planetary science by highlighting the diversity within habitable zones. Its size suggests that habitable conditions might exist under a variety of planetary structures, not confined to Earth-sized worlds. Models speculate whether it could hold vast oceans, thick clouds, or dense atmospheres that modulate surface temperatures, each scenario shaping the planet's potential to harbor life differently. Moreover, the case of Kepler-22b emphasizes the subtlety of planetary habitability. It is not solely the orbit or size that determines potential, but a complex interplay of stellar radiation, atmospheric composition, geological activity, magnetic fields, and more. These factors converge intricately, reminding us of the finely balanced conditions that make Earth hospitable and posing challenges in extrapolating habitability universally. Kepler-22b's discovery encouraged astronomers to sift through the Kepler catalog more diligently, identifying other small, potentially habitable worlds and advancing statistical estimates of Earth-like planets in the Milky Way. It has become emblematic of the exciting possibilities awaiting us as exoplanetary studies evolve. As we contemplate Kepler-22b's promise, we are reminded that the pursuit to find Earth's cousins is both a journey of technology and an exploration of fundamental questions about life's prevalence. This planet stands as a beacon illuminating the path ahead, a testament to human curiosity and the potential to one day find worlds that mirror our own in the vast cosmic expanse. From here, our voyage continues to worlds of violent winds and crystalline rains, to atmospheres whirling with exotic chemistry, as we explore the extremes of exoplanetary environments, each case study deepening our appreciation of the universe's extraordinary diversity. Among the myriad exoplanets discovered orbiting distant stars, HD 189733b stands out as one of the most vivid and striking examples of a world shaped by extreme and violent conditions. Often dubbed the fiery inferno or alien hell, this gas giant enchants and terrifies astronomers by showcasing exotic weather phenomena unlike anything in our solar system. Its characterization not only enriches our understanding of atmospheric science beyond Earth, but also reveals the remarkable diversity of planetary environments in the cosmos. In this case study, we take a deep dive into the mysteries of HD 189733b, exploring how this planet became known for its rain of glass and fierce winds, and what its features teach us about planets in the harsh embrace of their stellar hosts. HD 189733b orbits a K-type star approximately 64.5 light-years from Earth in the constellation Vulpecula. It was one of the first exoplanets detected through the transit method, allowing astronomers to capture detailed information about its size, orbit, and atmospheric properties. With a mass about 13% greater than Jupiter and a radius approximately 13% larger, it is classified as a hot Jupiter, a gas giant orbiting extraordinarily close to its star. Completing an orbit every 2.2 days, HD 189733b is subjected to intense stellar radiation, heating its day side to temperatures near 1200 degrees Celsius, about 2200 degrees Fahrenheit. One of the most remarkable features of HD 189733b is its extreme weather. Using the Hubble Space Telescope and later the Spitzer Space Telescope, scientists detected signatures of silicate particles in the planet's atmosphere. These tiny mineral dust grains condense into clouds, forming exotic hazes that give the planet its characteristic deep blue color, a stark contrast to the pale hues of Jupiter and Saturn. The blue tint arises from Rayleigh scattering, similar to Earth's sky, but on a much grander and more intense scale due to the presence of these atmospheric particles. However, the atmosphere also manifests phenomena beyond color. Despite the blistering heat, observations strongly indicate that HD 189733b experiences violent winds, estimated to blow at speeds exceeding 5,400 miles per hour, about 8,700 kilometers per hour. These supersonic gusts circulate heat from the scorching day side to the cooler night side, creating jet streams swirling around the planet. Such wind velocities dwarf anything experienced on Earth or within our solar system, a testament to the extreme dynamics imposed by the planet's tight orbit. Perhaps most astonishing is evidence suggesting that HD 189733b experiences rain, but not of water, rather of molten glass. Spectroscopic data reveals the presence of silicate particles capable of condensing and forming tiny droplets of glass rain in the cooler upper atmosphere. Driven by the furious winds, shards of this glass rain are thought to lash the planet, yielding a truly alien meteorological event. This extraordinary phenomenon highlights how different planetary chemistry and physics combine uniquely under such harsh conditions. The violent environment stems from HD 189733b's close proximity to its star, resulting in tidal locking, a state where one hemisphere perpetually faces the star, basking in relentless daylight, while the other side remains in permanent night. This configuration drives extreme temperature contrasts, fueling atmospheric circulation and complex weather patterns. Studying this planet's atmosphere unlocks insights into how heat redistribution operates on worlds drastically different from Earth. Additionally, the planet confronts intense stellar activity, including flares and high-energy radiation from its parent star. This radiation can ionize layers of the upper atmosphere, inducing magnetic interactions and possibly atmospheric escape, further influencing the planet's evolution. HD 189733b has been extensively observed across various wavelengths, from visible light to infrared, enabling detailed modeling of its atmospheric composition and dynamics. Scientists find that it likely hosts layers of clouds and hazes composed of exotic compounds, including silicates, iron, and possibly aluminum oxide, complicating traditional interpretations of atmospheric spectra and challenging modelers to reproduce its intricate features. The study of HD 189733b enriches our broader understanding of exoplanet atmospheres, especially regarding how atmospheric chemistry, temperature, and stellar impact converge to produce weather systems far removed from terrestrial experience. Its violent winds and glass rains testify to nature's boundless creativity and the variety of planetary environments beyond our solar system. Moreover, investigations into planets like HD 189733b illuminate the processes shaping gas giants broadly, including atmospheric escape, cloud formation, and thermal transportation, which have implications for planetary formation and evolution theories. As we reflect on the tempestuous character of HD 189733b, we stand reminded that the universe hosts more than static worlds. They are dynamic, ever-changing entities, shaped by both internal processes and their cosmic neighborhoods. Our next exploration will delve into the unseen companions of exoplanets, moons, and rings that add another dimension to the complexity and mystery of these distant systems, enriching the narrative of worlds beyond our own. Among the wonders of planetary systems that grace our universe, the presence of moons and ring systems adds a richness and complexity that often goes unnoticed but profoundly influences planetary environments. In our own solar system, moons like Earth's Luna and Jupiter's volcanic Io have immense significance, shaping tides, geology, and potentially even habitability. Similarly, rings like those encircling Saturn paint breathtaking celestial spectacles. Extending these concepts beyond our Sun, the study of exomoons and rings, unseen companions orbiting distant exoplanets, opens a new dimension in our understanding of planetary formation, dynamics, and the subtle clues they offer in the search for life. Detecting exomoons and rings is a frontier at the cutting edge of astrophysics, fraught with challenges stemming from their relatively small size and faint signals. Unlike their planets, which can be detected through discernible wobbles or transits, moons and rings cast much more subtle signatures. Yet, advancements in observational techniques and the deployment of powerful telescopes have brought these elusive companions within our scientific reach. One of the primary methods for inferring the existence of exomoons involves scrutinizing transit light curves for anomalies. When a planet passes in front of a star, the slight dip in brightness yields information about its size and orbit. A moon orbiting that planet can cause additional dips, distortions, or timing variations known as transit timing variations, TTVs, and transit duration variations, TDVs. Careful analysis of these subtle cues in the light curve data has suggested possible exomoon candidates, sparking excitement about future confirmations. Similarly, ring systems around exoplanets can be suspected when transit data shows unusual ingress and egress features, indicating that something more complex than a simple spherical planet is obscuring the star's light. Rings increase the effective cross-sectional area, causing characteristic patterns such as prolonged or asymmetric dips. These signals are intricate to decode and require precise, repeated observation, but detecting rings offers clues to planetary rotational history, age, and formation processes. Beyond detection, the potential significance of exomoons and rings is immense. Moons can influence a planet's habitability by stabilizing its axial tilt, contributing to tidal heating, and even generating magnetic environments that protect atmospheres from stellar winds. Some exomoons themselves might be habitable or host subsurface oceans, as seen with Jupiter's Europa or Saturn's Enceladus in our own system. Ring systems, while often transient on cosmic timescales, provide insights into past collisions, satellite formation, and dust and debris distribution. A prominent ring system can affect planetary climates by modulating reflected or absorbed light, and can reveal dynamical interactions with satellites. While direct detection remains elusive, upcoming missions and next-generation telescopes, such as the James Webb Space Telescope and future space-based observatories, hold promise for making definitive observations. These technologies, combined with improved data analysis methods powered by machine learning, may soon routinely uncover these unseen companions. Scientific interest in exomoons and rings extends beyond discovery, touching on questions about the prevalence of complex planetary systems and the potential niches where life might arise. The interplay between planets, their moons, and rings weaves a complex tale of gravitational balance, formation histories, and environmental factors, the unseen companions that shape the destiny of worlds. The study of exomoons and rings enriches our cosmic perspective, reminding us that planets seldom walk alone. Their satellites and surrounding debris sometimes tell stories as captivating as the planets themselves, expanding the horizons of exoplanetary science into new and thrilling territories. As our capabilities grow sharper and our observations more refined, we approach a future where the hidden worlds orbiting exoplanets, their moons and magnificent rings, emerge from the shadows to illuminate the breadth and depth of planetary diversity in our galaxy. From these companions, we gain new windows into the dynamics, history, and potential habitability of the alien worlds we continue to discover. In the vast, star-studded canvas of our galaxy, the search for life beyond Earth stands as one of humanity's most profound and enduring quests. This pursuit extends far beyond cataloging planets. It embarks on the delicate art of detecting subtle signs, biosignatures and technosignatures that may reveal the presence of life or even intelligent civilization on distant worlds. In this chapter, we delve into the science, challenges, and excitement surrounding the detection of these elusive signals, unfolding the elaborate dance between the universe's mysteries and human ingenuity. To begin, biosignatures refer to any substance, such as an element, molecule, or process, that provides scientific evidence of past or present life. In the context of exoplanets, biosignatures often focus on atmospheric gases or surface features that suggest biological activity. For example, the simultaneous presence of oxygen and methane in a planet's atmosphere is compelling because these gases react chemically and would not coexist in large amounts without continuous replenishment, potentially indicating biological processes. Detecting such biosignatures requires precise measurements of exoplanetary atmospheres. The transit method, where a planet passes in front of its star, provides an opportunity to dissect starlight filtered through a planet's atmospheric layers. Spectroscopic studies can identify characteristic absorption lines corresponding to molecules like water vapor, ozone, oxygen, methane, and even complex organic compounds. Future observatories, particularly the James Webb Space Telescope, and proposed missions like LUVOIR, Large UV Optical IR Surveyor, aim to enhance our ability to analyze these molecular fingerprints across a broader range of exoplanets, including Earth-sized worlds in habitable zones. Surface biosignatures, while more challenging to detect, could include pigmentation from photosynthetic organisms or large-scale changes in reflectance patterns across a planet's surface, clues that might someday be unveiled with high-resolution imaging technologies. Such features, if found, would provide extraordinary insights into biological activity akin to Earth's verdant landscapes. Beyond biosignatures lie technosignatures, indicators of technology or intelligent life. These include artificial signals or structures potentially detectable at vast interstellar distances. Classical examples are narrow-band radio emissions, laser pulses, or unusual optical light patterns that natural astrophysical processes cannot easily imitate. Searches for technosignatures are core to the search for extraterrestrial intelligence, SETI programs, which employ radio telescopes and optical observatories to scan the skies for deliberate or accidental transmissions from advanced civilizations. Recent expansions in search strategies probe even more exotic technosignatures, including megastructures, hypothetical colossal constructs built around stars to harness energy, detectable through peculiar dips or irregularities in stellar brightness. Systems like the enigmatic Tabby's star, KIC 8462852, have sparked interest and debate about the potential of such phenomena. though natural explanations often offer more parsimonious accounts. Distinguishing genuine biosignatures or technosignatures from abiotic processes or instrumental artifacts demands rigorous analysis and confirmation. Planetary atmospheres can produce misleading signals through photochemistry, volcanic activity, or atmospheric escape mechanisms. Similarly, radio frequency interference from Earth-based sources challenges the authenticity of candidate technosignals. Consequently, the scientific community emphasizes multiple lines of evidence and independent verification before asserting detection. Furthermore, the diversity of planetary environments, ranging from tidally locked worlds around red dwarfs to ancient planets orbiting old stars, invites a broadened perspective on possible signatures of life. Life may utilize different biochemistries or technologies, producing less familiar or as yet unknown markers. Consequently, astrobiologists also pursue theoretical models predicting alternative biosignatures and technosignatures, expanding the horizons of what signals to seek. Engaging the public and citizen scientists in this cosmic search enhances capabilities. Projects like SETI Home enable individuals worldwide to contribute computing power to analyze vast datasets, democratizing space exploration in an unprecedented way. The hunt for life signs, both biological and technological, carries profound philosophical significance, compelling us to reflect on our origins, uniqueness, and future in the cosmos. With each new exoplanet discovery and each refinement in observational technique, the probability of detecting signatures consistent with life slowly shifts from speculation to achievable endeavor. As our instruments grow ever more sensitive and our analytical frameworks more sophisticated, the tantalizing prospect of identifying life's markers on distant worlds moves closer to reality. The journey is meticulous and humbling, reminding us that the universe's silent expanse may one day echo with signs that we are not alone, inspiring generations to continue reaching upward toward the stars. Among the many stellar families that grace our cosmic neighborhood, red dwarfs stand out for their abundance and intriguing planetary companions. While these small, cool stars might seem unassuming compared to behemoths like our Sun, their planetary systems offer fertile ground for discovery, especially in the search for worlds that might harbor life. One such stellar system has captured both scientific attention and public imagination: the TRAPPIST-1 system, home to 7 Earth-sized planets, affectionately known as the Seven Sisters. This chapter invites you on a voyage to explore these fascinating worlds and understand why exoplanets orbiting red dwarfs hold special promise and peculiar challenges in the cosmic quest. TRAPPIST-1 is an ultra-cool red dwarf star located approximately 40 light-years from Earth in the constellation Aquarius. With about 9% of the Sun's mass and less than 0.1% of its luminosity, it is dimmer and cooler, emitting a faint but steady glow primarily in the infrared part of the spectrum. Despite its modest stature, TRAPPIST-1 boasts a remarkable planetary retinue: 7 terrestrial-sized planets, all closer to their star than Mercury is to the Sun, making it one of the most compact and orderly planetary systems discovered to date. The discovery of the TRAPPIST-1 planets, initially revealed in 2016 and then expanded upon in subsequent years through observations by NASA's Spitzer Space Telescope and numerous ground-based observatories, marked a milestone. The ensemble includes planets ranging from roughly 0.75 to 1.13 times Earth's radius, many residing within or near the star's habitable zone, the narrow orbital band where temperatures might allow liquid water to exist. These compact orbits mean the TRAPPIST-1 planets tightly circle their star in periods ranging from just 1.5 to nearly 18 days. The closeness leads to fascinating gravitational interactions, which scientists use to measure planetary masses and densities through transit timing variations. This precision reveals that some planets in the system possess densities consistent with rocky compositions, imbued with potential for water and atmospheres. Yet, the peculiarities of red dwarf stars impose unique characteristics on their planetary companions. TRAPPIST-1 emits strong stellar flares and high-energy radiation, especially in its youthful years, which could erode planetary atmospheres or impact surface conditions. Additionally, the planets are likely tidally locked, showing the same face perpetually to their star, resulting in stark contrasts between eternal day and night hemispheres. Despite these factors, climate models propose that atmospheric and oceanic dynamics could redistribute heat, potentially stabilizing climates and preserving habitable environments. The compactness and multiplicity of the TRAPPIST-1 system make it a natural laboratory for studying planetary formation, orbital dynamics, and habitability around low-mass stars. Its planets stand among the best candidates for future atmospheric characterization with next-generation telescopes such as the James Webb Space Telescope, which aim to detect atmospheric gases, search for biosignature molecules, and probe oceanic or geological activity indirectly. Beyond scientific intrigue, the TRAPPIST-1 system challenges and expands our conceptions of where life might thrive in the universe. It fuels the tantalizing possibility that habitable, Earth-sized worlds might be far more common around red dwarfs, which constitute about 75% of all stars in the Milky Way. However, many mysteries remain. Are these worlds equipped with stable, life-supporting atmospheres after billions of years under stellar tempest? Do they harbor oceans, continents, or complex chemical cycles? How does the star's unique environment shape their evolutionary pathways? These questions propel ongoing observations and intricate modeling. The Seven Sisters orbiting their modest star invite us to dream boldly, to imagine life under alien suns, in worlds orbiting stars far smaller and cooler than our own. They embody the wondrous diversity and cosmic generosity of planetary formation, reminding us that even the faintest stars can host worlds of immense potential. As our exploration continues, TRAPPIST-1 stands as a beacon, guiding us toward the next revelations about planet diversity, atmospheric mysteries, and the delicate balances necessary for life in the universe's sprawling tapestry. In the cosmic dance of planets around stars, one intriguing phenomenon stands out for its graceful yet enigmatic nature: tidal locking. This celestial ballet results in worlds that always show the same face to their stars, a condition known as tidal locking. Such tidally locked planets present an elegant paradox, simultaneously familiar and alien. As we explore this concept, we will uncover the remarkable implications tidally locked worlds have for planetary climates, atmospheres, and the prospects for life, illustrating both their strange beauty and scientific significance. Tidal locking arises from gravitational interactions between a planet and its host star. Over time, the gravitational pull creates tidal bulges on the planet. Frictional forces between these bulges and the planet's rotation gradually synchronize the planet's rotational period with its orbital period. As a result, the same hemisphere perpetually faces the star, bathing in constant daylight, while the opposite side resides in eternal darkness. This phenomenon is not uncommon. Many moons in our solar system, including our own moon orbiting Earth, are tidally locked. Among exoplanets, particularly those orbiting red dwarfs or other low-mass stars, tidal locking is expected to be frequent because the habitable zone lies close to the star, where gravitational forces are stronger and synchronization occurs relatively quickly in astronomical terms. The climate on tidally locked planets is unlike anything on Earth. With one side perpetually heated and the other plunged into darkness, stark temperature gradients develop. The day side can scorch under uninterrupted stellar radiation, while the night side chills in frigid darkness. However, atmospheric circulation and ocean currents, if present, may redistribute heat, softening these extremes and potentially creating a habitable twilight zone or terminator region near the day-night boundary. Atmospheric dynamics on tidally locked worlds can be complex and vibrant. Winds may howl at extraordinary speeds, carrying heat from the star-facing side to the dark hemisphere. Cloud formation can be intense, possibly leading to thick cloud cover on the day side that reflects significant stellar radiation, acting as a natural thermostat. Meanwhile, the night side's cold traps might cause atmospheric components, like water vapor, to condense into ice. The potential habitability of tidally locked planets is a topic of active research and debate. While eternal daylight and darkness might appear inhospitable, models suggest that life could thrive in the temperate zones near the terminator or in subsurface environments. Unique ecosystems adapted to extreme light cycles or biochemistries relying on tidal forces and chemical gradients could flourish. Examples of tidally locked exoplanets abound. The TRAPPIST-1 system's several Earth-sized worlds are likely tidally locked, presenting laboratories to study such environments. Additionally, planets like Proxima Centauri b, orbiting the nearest star to the Sun, may be tidally locked, making our nearest extrasolar neighbor a prime candidate for this phenomenon. The strange elegance of tidally locked worlds invites us to reconsider assumptions rooted in Earth's dynamics, challenging us to envision life and climates under unearthly conditions. They emphasize the diversity of celestial environments and broaden the scope of our search for habitable worlds. As we continue, understanding tidally locked planets will inform studies of ancient worlds, mysterious megastructures, and the broader quest to comprehend the endless varieties of planets that pepper our galaxy, reaffirming the boundless complexity and beauty woven into the fabric of the universe. Among the countless planets sprouting around stars throughout the Milky Way, a special class piques our cosmic curiosity: ancient worlds older than our own sun. These time-worn planets, potentially billions of years beyond Earth's age, offer glimpses into the deep history of planetary formation and the broader evolution of the galaxy itself. They stand as silent witnesses to epochs long past, providing us with valuable insights and profound questions about planetary longevity, the nature of habitability over cosmic timescales, and perhaps even the early conditions for life in the universe. Our Sun is approximately 4.6 billion years old, but stars, and by extension their planets, span a remarkable age range. Some stars in the Milky Way reside in the galactic halo, or thick disk, belonging to ancient populations formed during the early stages of the galaxy's life. Orbiting these elder stars, ancient planets may have formed when the universe was a very different environment, with lower abundances of heavy elements known as metals, which are essential building blocks for rocky planets and biochemical complexity. Finding and studying ancient exoplanets is a scientific challenge. Their stars tend to be faint and often metal-poor, making it tricky to detect and characterize orbiting worlds. However, advances in telescopes and detection methods have started to uncover such systems. For instance, the planet PSR B/2026b, orbiting a pulsar and a white dwarf in a globular cluster, is often called the Methuselah planet, estimated to be over 12 billion years old, making it one of the oldest known planets. These primordial worlds prompt profound questions. How did planet formation proceed in an early, metal-poor universe? Can rocky planets with complex chemistry form in such environments? Do ancient planets retain atmospheres and potential habitability over such vast timescales? These queries support the exploration of planetary formation models across different galactic epochs. Ancient planets also raise fascinating considerations about biological evolution and the potential window for life. If life emerged on a planet billions of years older than Earth, it might have had a head start in the cosmic timeline. This tempts the imagination with the tantalizing possibility of advanced biospheres or even civilizations that predate humanity by eons. On the flip side, these worlds have also endured dynamic galactic events, supernovae, gamma-ray bursts, gravitational encounters that could threaten atmospheric integrity and biological continuity. Understanding how ancient planets survive such hardships informs the limits and robustness of habitability. Studying the atmospheres and physical characteristics of ancient planets is essential for unraveling their stories. Metallicity affects not only planet composition, but also atmospheric retention and chemistry, influencing climate and surface conditions. Technologies like the James Webb Space Telescope and future missions will enable detailed observations of stellar populations hosting the oldest planets, probing for these markers. The quest to find and comprehend ancient worlds enriches our appreciation of the universe's vast temporal dimension. These planets serve as bridges connecting us to the universe's youth, illuminating the long and complex saga of planetary evolution against the backdrop of a changing galaxy. As we reflect on these ancient worlds, they remind us that the cosmos is not only vast in space, but deep in time, holding realms older than our sun, with stories spanning billions of years that invite us to continue seeking answers beyond the horizon of our own existence. Our journey through the mysteries of exoplanets now turns toward a more enigmatic chapter: the investigation of mysterious megastructures, phenomena that challenge the borders between natural and perhaps artificial constructs, stirring the imagination and scientific inquiry into realms both extraordinary and uncertain. In the panorama of exoplanetary science, few topics ignite as much fascination and debate as the mysterious megastructures, enigmatic phenomena detected through unusual light variations around distant stars that spark a tantalizing, if speculative, question. Are these the signs of alien civilizations or extraordinary natural events? This chapter embarks on an exploration of these cosmic puzzles, delving into the observations, interpretations, and the cautious balance between imagination and scientific rigor that defines our engagement with these mysterious stellar anomalies. The story of mysterious megastructures catapulted into public consciousness with the discovery of KIC 8462852, popularly known as Tabby's star, named after astronomer Tabitha Boyajian. Unlike the predictable and periodic dimming one might expect from a transiting exoplanet, Tabby's star exhibits irregular, dramatic dips in brightness, some plunging as much as 22%. These dimming events lack clear periodicity and vary in duration and intensity, defying easy classification. Initial speculations about Tabby's star include swarms of comets, dense clouds of dust, disrupted planetary debris, or intrinsic stellar variability. However, the absence of a definitive natural explanation has led to fringe but captivating hypotheses involving alien megastructures, vast extraterrestrial constructions such as Dyson spheres or swarms designed to harvest a star's energy. While mainstream science regards such speculation cautiously, these ideas underscore the profound mystery and allure of the observations. A Dyson sphere, first proposed by physicist Freeman Dyson in 1960, is a hypothetical megastructure encompassing a star to capture its energy output, possibly built by an advanced civilization. Detecting such a structure would manifest as unusual stellar light curves or significant infrared excess. The star's energy absorbed and re-radiated as heat by the structure's surface. To date, no conclusive infrared signatures consistent with such constructs have been observed around Tabby's star or similar candidates. Beyond Tabby's star, surveys scanning thousands of stars have occasionally encountered other atypical dimming patterns or unexplained variabilities, fueling ongoing research into their origins. The data collected often necessitate advanced models of stellar astrophysics, including complex dust geometries, gravitational interactions, or magnetically driven phenomena, emphasizing the universe's capacity for natural complexity. Scientists employ multifaceted approaches to decode these phenomena. Continuous photometric monitoring, spectroscopic analysis, and multi-wavelength observations test competing hypotheses, aiming to differentiate between natural and artificial causes. The scientific community maintains rigorous skepticism, prioritizing natural explanations supported by evidence, while remaining open to anomalies that challenge current understanding. These investigations transcend pure astrophysics, intersecting with the search for extraterrestrial intelligence, SETI, which vigilantly listens for possible technosignatures, signals or artifacts indicative of intelligent activity. Unusual light curves prompt targeted SETI observations, though thus far, no confirmed alien signals have emerged. The intrigue surrounding mysterious megastructures captivates the imagination, serving as fertile ground for speculative fiction and philosophical reflection regarding humanity's place in the cosmos. They remind us of the profound vastness and complexity of the universe, where natural phenomena may elude current paradigms, and where the possibility, however remote, of other intelligences provokes humility and curiosity. As our instruments and methods grow more sophisticated, and as surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, and next-generation telescopes begin operations, we may encounter more of these enigmatic signals. Each discovery challenges researchers to refine models and expand the horizons of astrophysical knowledge. Ultimately, mysterious megastructures embody the thrilling edge of exoplanetary and astrophysical research, a realm where observation meets imagination, and where every shadow, every dip in starlight, beckons us to uncover deeper truths about the universe's architecture and the possibilities it harbors. Our journey next leads us into the collaborative spirit fueling exoplanet exploration, the vibrant world of citizen science and community engagement, where shared curiosity empowers discovery and advances our understanding of the cosmos. In the grand quest to explore the cosmos and uncover the secrets of distant worlds, one of the most inspiring developments has been the rise of citizen science, an empowering movement that invites curious individuals from all walks of life to contribute meaningfully to astronomical research. The discovery and study of exoplanets have uniquely embraced this collaborative spirit, creating a vibrant community where professional scientists and enthusiastic amateurs join forces, harnessing collective dedication and ingenuity to accelerate the search for hidden worlds. This chapter explores how citizen science has become a vital partner in exoplanet exploration, the various ways you can get involved, and the transformative impact such participation carries for both science and society. At the heart of citizen science is the democratization of scientific inquiry. The availability of extensive digital data, coupled with web-based platforms and sophisticated analysis tools, has opened doors for anyone with an internet connection to sift through real astronomical observations. Projects like Planet Hunters, Exoplanet Explorers, and NASA's Backyard Worlds utilize data from missions such as Kepler, TESS, and others, inviting volunteers to examine light curves, identify potential planetary transits, or spot subtle signals indicative of exoplanets and related phenomena. Unlike automated algorithms, human eyes excel at recognizing patterns, anomalies, and irregularities that computers might miss or misclassify. Volunteers have made significant contributions, including the identification of new exoplanet candidates, the discovery of intriguing astrophysical features, and the flagging of unusual data worthy of further investigation. The discovery of exoplanet KIC 8462852's unusual light dips, for instance, was greatly aided by public interest and examination. Participating in citizen science often requires little more than patience, curiosity, and willingness to learn. Online tutorials and forums provide supportive resources, enabling newcomers to develop skills in data interpretation, statistical analysis, and even basic astrophysics. For educators and students, these projects offer exceptional hands-on experience that transcends textbooks, fostering genuine engagement with cutting-edge science. Beyond data analysis, citizen scientists contribute through visual artwork, writing, advocacy, and public outreach, helping to inspire broader awareness and enthusiasm for exoplanet research. This weaving of diverse talents and perspectives enriches the field culturally and intellectually. Importantly, citizen science fosters a powerful sense of community. Enthusiasts worldwide connect through online platforms, social media, and conferences, exchanging ideas, celebrating discoveries, and supporting one another in their shared passion. This network breaks down traditional barriers, making the cosmos a collective human endeavor. The impact of citizen science on exoplanet research is measurable and growing. The volume of data produced by modern observatories is staggering, surpassing what professional astronomers alone can process efficiently. Collaborative human analysis accelerates discovery rates, improves data quality, and guides the allocation of telescope time for follow-up studies. Moreover, citizen science exemplifies the philosophy that science is not merely for specialists, but is a universal pursuit. It empowers individuals to take an active role in expanding humanity's understanding of our place in the universe, nurturing a personal connection to the stars and the planets beyond. Looking ahead, advances in artificial intelligence and machine learning will continue to enhance data processing, but human intuition and creativity will remain indispensable, particularly in recognizing unexpected phenomena and fostering innovative hypotheses. Citizen science will coexist with these technologies, continuing to invite the public's eyes and minds into the great adventure. In conclusion, the exoplanet community's embrace of citizen science demonstrates how collaboration across boundaries fuels progress and creates opportunity. By joining this global effort, you don't merely observe from afar. You become an integral part of humankind's voyage to discover alien worlds. Whether helping identify planetary candidates or sharing knowledge and enthusiasm, every contribution shapes our collective dream. As our story unfolds, we next consider the future horizons of exploration with powerful tools like the James Webb Space Telescope and beyond, poised to deepen our insights and broaden our cosmic horizons. As we stand at the threshold of a new era in the exploration of distant worlds, the future of exoplanet research is radiantly illuminated by groundbreaking technologies that promise to transform our understanding of planets beyond our solar system. Chief among these is the James Webb Space Telescope, JWST, launched to succeed and expand upon the pioneering discoveries of its predecessors, combined with a cohort of next-generation observatories and missions that will unveil realms previously hidden from us. This chapter embarks on an expansive look at these anticipated advancements, revealing how they promise to deepen, refine, and possibly revolutionize our cosmic perspective. The James Webb Space Telescope, often called the successor to Hubble, is uniquely poised to probe the atmospheres, surfaces, and thermal properties of exoplanets with unmatched sensitivity and breadth. Operating primarily in the infrared, JWST penetrates cosmic dust and captures the faint glimmers of heat from planets billions of miles away. This spectral window is particularly crucial for detecting molecules like water vapor, carbon dioxide, methane, and ozone, key markers in the quest for habitability and potential biosignatures. JWST's powerful instruments, such as the near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument, MIRI, enable high-resolution spectroscopy during planetary transits and eclipses, allowing scientists to parse the exquisite chemical fingerprints of exoplanetary atmospheres. This facilitates detailed characterization of countless known exoplanets, from scorching hot Jupiters to temperate, rocky super-Earths, many orbiting within their stars' habitable zones. Complementing JWST are upcoming and proposed missions and observatories designed to expand the breadth and depth of exoplanet exploration. NASA's Transiting Exoplanet Survey satellite, TESS, has already surveyed the entire sky to identify exoplanets orbiting bright, nearby stars, establishing a vital catalog of candidates primed for atmospheric follow-up by JWST and other telescopes. The European Space Agency's Atmospheric Remote Sensing Infrared Exoplanet Large Survey, ARIEL, slated for launch in the late 2020s, will embark on a comprehensive survey of exoplanet atmospheres, aiming to uncover correlations between planetary compositions, stellar properties, and formation pathways. On the horizon stand the Extremely Large Telescopes, ELTs, ground-based giants like the Extremely Large Telescope in Chile, the Giant Magellan Telescope, and the 30-meter telescope. Equipped with advanced adaptive optics and spectrographs, these observatories will deliver spatial resolution and sensitivity up to now unimaginable from Earth, directly imaging exoplanets and probing their light for atmospheric signatures, weather, and perhaps even surface features. The combination of space and ground-based capabilities promises a synergistic approach that maximizes the scientific yield. The innovations don't stop with hardware. Advances in data analysis, artificial intelligence, and modeling are crucial in extracting faint planetary signals from noisy data and simulating complex planetary environments. These computational breakthroughs will help unravel the intricate weather patterns, cloud dynamics, and potential biosignatures of distant worlds with greater accuracy. Looking further ahead, visionary missions such as NASA's Habitable Exoplanet Observatory, HABEX, and the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, concept promise direct imaging missions with the capacity to capture images of Earth-like planets, analyze their atmospheres in unprecedented detail, and perhaps even map surfaces for oceans and continents. These ambitious projects symbolize humanity's profound leap towards truly characterizing potentially habitable worlds. Moreover, probe-class missions conceptually designed for interstellar precursor studies hint at a future when exoplanetary systems might be studied up close, transcending current limitations imposed by light years of distance. Crucially, the future of exoplanet exploration is not purely a matter of technology, but an evolving ethos of openness, interdisciplinary collaboration, and public engagement. As data becomes ever more abundant, global cooperation among astronomers, planetary scientists, chemists, and biologists will be essential in synthesizing knowledge and interpreting findings within broader cosmological and astrobiological contexts. The unfolding narrative suggests that within just a few decades, humanity could move from merely cataloging exoplanets to discerning their compositions, climates, and signs of life. A journey from distant specks of light to familiar, albeit alien, worlds with rich environments and perhaps even biotic landscapes. In this exciting future, the James Webb Space Telescope and its successors stand as harbingers of boundless discovery, inviting us to explore deeper into the night, pushing the boundaries of human knowledge and nurturing our enduring fascination with the mysteries beyond our star. This progress revives our cosmic perspective and fortifies the eternal quest to understand the universe and our place within it, setting the stage for imagining life on distant shores, the subject of our next chapter. As we gaze toward the vastness beyond our solar system, teeming with countless planets of bewildering variety, our imagination naturally wanders to the tantalizing question of life beyond Earth. Dreaming of distant shores, alien landscapes bathed in unfamiliar light, invites us to envision what life might look like under different suns on worlds shaped by distinct histories, chemistry, and physics. This chapter embraces the art and science of imagining life on other worlds, charting the possibilities and grounding them in our growing understanding of the diversity and complexity of exoplanets. Our experiences on Earth provide the foundational lens through which we imagine extraterrestrial life. Yet, as we uncover planets with exotic orbits, atmospheres suffused with unusual gases, or climates shaped by tidal locking or ancient origins, the boundaries of our imagination must expand. Life elsewhere may not mirror terrestrial life in appearance, metabolism, or behavior, but could arise in forms adapted to their local environments, displaying a spectrum of biochemistries and ecosystems that challenge our familiar concepts. Consider a tidally locked planet orbiting a red dwarf star, where one hemisphere endures eternal daylight and the other eternal night. Life in such locales might flourish along the terminator, the twilight zone, where temperatures moderate and light is dim but steady. Organisms could develop biological rhythms attuned to this singular illumination, potentially harnessing light through novel photosynthetic pigments tuned to longer wavelengths. On ocean worlds blanketed by endless seas beneath dense atmospheres, life might exist beneath the surface, shielded from harsh stellar radiation. Complex underwater ecosystems could rely on chemosynthesis near volcanic vents, independent of sunlight. These ecosystems echo speculations about Europa or Enceladus in our own solar system, emphasizing how life's adaptability might transcend traditional habitable zones. Atmospheric chemistry plays a vital role in shaping possible biospheres. Planets with atmospheres rich in methane, carbon dioxide, or even exotic gases like hydrogen sulfide could support life forms metabolizing these compounds. The presence of greenhouse gases modifies surface temperatures and climate stability, influencing where life could find niches. The physical structure of life is another horizon for imagination. Lower gravity worlds may host taller, more delicate organisms. High radiation environments might favor protective biochemistries or underground habitats. Evolutionary pressures could produce bioluminescence, camouflage, or novel sensory modalities unlike anything on Earth. Humanity's portrayal of alien life in literature and art expands this vision, blending scientific plausibility with creative flourish. These narratives shape and are shaped by discoveries, inspiring public interest and stimulating interdisciplinary dialogues, bridging biology, chemistry, and astronomy. Scientific endeavors complement these creative explorations. Research into extremophiles, organisms thriving in Earth's harshest environments, offers analogs for imagining life's possibilities under alien conditions. Astrobiologists consider the potential for life not merely as a binary presence, but as diverse expressions of biological processes across the cosmos. Moreover, imagining life on other worlds sharpens our sense of stewardship for our own planet. It reinforces the rarity and fragility of conditions fostering life, instilling motivation to cherish and protect Earth's biosphere. As telescopes sharpen and space missions reach farther, the line between imagination and observation narrows. One day, glimpses of life's signatures may illuminate distant skies, turning dream into discovery. From dreams of distant shores, our exploration proceeds to confront one of the most profound cosmic mysteries: the silence amid countless stars, framed by the Fermi paradox. Where is everybody? The next chapter unfolds this puzzle, deepening our reflection on the universe's strange quietude and humanity's place within it. When we peer into the night sky and consider the vastness of the cosmos, teeming with billions of stars, many surrounded by planets that could harbor life, one profound and unsettling question arises. If the universe is so richly populated with the potential for life, then where is everybody? This perplexity is known as the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" This chapter delves into this paradox, exploring the tension between high estimates for extraterrestrial life and the conspicuous absence of conclusive evidence or contact, a silence that's both enigmatic and deeply thought-provoking. The paradox centers around two basic observations. First, stars are numerous and old, and planets appear common, many within habitable zones. The sheer numbers and timescales imply, statistically, that intelligent life should have arisen multiple times in the galaxy. Second, despite decades of searching, humanity has yet to detect definitive signs of alien civilizations. No verified radio transmissions, no artifacts, no clear megastructures or communications. This contradiction invites a multitude of possible resolutions, each reflecting different perspectives on astrophysics, biology, sociology, and technological progression. Among the most discussed explanations is the notion that advanced civilizations might self-destruct, fall victim to environmental disasters, or technological catastrophes, extinguishing themselves before expanding widely. A sobering concept sometimes called the Great Filter. Alternatively, civilizations might be rare or short-lived, or life itself might be extraordinarily difficult to develop complexity beyond simple organisms. Others propose that intelligent species may choose deliberate silence, avoiding contact to prevent harm or interference, a cosmic version of quarantine often termed the zoo hypothesis. Technological limitations in our searches further complicate the picture. Perhaps we are listening to the wrong signals, at the wrong frequencies, or using insufficiently sensitive instruments. It's also plausible that extraterrestrial intelligences communicate in ways we cannot yet comprehend, or with technologies beyond our current grasp. Moreover, the vastness of space and the enormous timescales involved imply natural delays in the arrival or detection of signals or probes. Even if life exists extensively, interstellar travel and communication may be prohibitively difficult or rare. An especially intriguing angle considers the possibility of non-expansionist civilizations, focused inward or inhabiting virtual realities, limiting outward visibility. Alternatively, advanced societies might have transcended physical forms, becoming undetectable by methods we imagine. Despite these uncertainties, scientific endeavors continue searching for biosignatures and technosignatures with increasing sophistication. The study of atmospheric gases, alien megastructures, and anomalous signals all bear hope for eventual detection. Philosophically, the Fermi paradox prompts reflection on humanity's uniqueness, responsibilities, and destiny. Are we the first, the only, or simply early participants in a grand cosmic story? It compels us to ponder the future of our civilization and the ethical considerations in seeking contact. Ultimately, the Great Silence is not just a scientific problem, but an invitation, a challenge to extend our inquiry, improve technological capabilities, and deepen our understanding of life's nature. It strengthens our resolve to explore and to listen, expanding our quest from mere search into a profound dialogue between science, philosophy, and hope. As we ponder this silence stretching across the stars, our journey continues into how the discovery of exoplanets reshapes human culture, perspectives, and the very narratives through which we understand the universe and ourselves. The discovery of exoplanets has profoundly reshaped not only our scientific understanding of the cosmos, but also our cultural, philosophical, and existential perspectives. Beyond the thrill of uncovering new worlds, these distant planets invite us to reevaluate humanity's place in the universe, challenge long-held beliefs, and inspire new ways of thinking about life, identity, and our shared destiny. This chapter explores how exoplanet discoveries have permeated our culture, influencing art, literature, philosophy, and collective consciousness, illuminating the enduring human quest to find connection in the vast cosmic expanse. Historically, humanity's conception of the universe was Earth-centric, reinforced by religious and philosophical traditions across civilizations. The Copernican revolution displaced Earth from the universe's center, yet the solar system remained our known cosmic neighborhood for centuries. Now, exoplanets have expanded that neighborhood exponentially, revealing a galaxy crowded with worlds of diverse sizes, compositions, and environments, each a potential cradle for life. This realization dissolves the singularity of Earth and challenges anthropocentric views, inviting humility and wonder. In art and literature, the surge of exoplanet discovery has inspired a renaissance of creativity. Sci-fi narratives grapple with the implications of alien life and the challenges of interstellar exploration, ranging from the hopeful to the cautionary. Works like Carl Sagan's Contact and contemporary media explore human encounters with other worlds and intelligences, often reflecting contemporary hopes, fears, and ethical questions. Visual arts now depict imagined landscapes of exoplanets, worlds with twin suns, vast oceans, endless deserts, or skies of unfamiliar colors, fostering a sense of awe that transcends scientific discourse. Philosophically, the awareness of myriad distant worlds provokes questions about the uniqueness of life, consciousness, and morality. If life is widespread, what does that imply for the meaning of our existence? How should we understand our responsibilities toward extraterrestrial environments and potential life forms? These inquiries extend beyond science into theology, ethics, and the humanities, encouraging interdisciplinary dialogue and expanding the scope of human inquiry. Culturally, the discovery of exoplanets has bridged borders, catalyzing shared global curiosity. The collective fascination with the cosmos fosters a sense of unity and collective identity transcending nationality, language, and belief. As people worldwide watch the announcements of new exoplanets or participate in citizen science projects, they engage in a shared human story, one that connects us with the universe and with each other. Education and outreach efforts leverage exoplanet discoveries to invigorate interest in STEM fields, inspiring new generations to seek careers in science, technology, engineering, and mathematics. This inspiration has practical societal benefits, driving innovation and cultivating a scientifically literate public. Moreover, the exploration of exoplanets challenges humanity to think critically about sustainability and stewardship of our own planet. Recognizing Earth as one of countless worlds underscores the fragile uniqueness of our environment, fostering urgency in addressing climate change, biodiversity loss, and environmental degradation. On a personal level, contemplation of distant worlds can encourage reflection, humility, and awe, dimensions often described as the cosmic perspective. This profound shift encourages people to consider the interconnectedness of life and the universality of existence, contributing to psychological well-being and a broadened worldview. Finally, the cultural impact of exoplanets feeds back into science itself, shaping funding priorities, research agendas, and international collaborations. Public enthusiasm invites policymakers to support ambitious missions and technologies, accelerating discovery and expanding humanity's reach. In essence, exoplanets do more than populate star charts. They populate our imaginations, philosophies, and cultures. They challenge us to envision new possibilities, reconsider our place in the cosmos, and embrace the enduring mystery and beauty of the universe. As we move forward, this enriched cultural context sets the stage for the endless quest, the ceaseless drive to understand, explore, and connect. The mystery of exoplanets thus becomes a mirror reflecting our deepest aspirations and fears, shaping the destiny of humanity amid the stars. The discovery and study of exoplanets have ushered humanity into an extraordinary epoch, a relentless quest to understand not only distant worlds, but also the fundamental nature of the universe and our place within it. As we culminate this journey through the cosmos, reflecting upon the myriad discoveries, mysteries, and insights exoplanets offer, we find that the quest is not merely about cataloging alien planets, but about embracing the boundless curiosity and humility that drives scientific exploration itself. Exoplanets teach us the universe is far more diverse and intricate than our Earth-centric perspectives once imagined. Worlds of unthinkable extremes, scorching hot Jupiters, mysterious rogue planets adrift in darkness, tidally locked siblings bathed in eternal light and shadow, challenge our conventional ideas, pushing the boundaries of planetary science and atmospheric chemistry. We learn that planetary systems do not all follow the neat blueprint once believed, but are shaped by complex, often chaotic processes that create a cosmic kaleidoscope of possibilities. The hunt for life around other stars, guided by biosignatures and technosignatures, reflects humanity's quintessential hope and ambition. It expands our understanding of life itself, prompting us to conceive of existence in forms and conditions vastly different from those on Earth. This profound expansion enriches biology, chemistry, and philosophy, reminding us that life's narrative might be far richer and more universal than previously conceived. Furthermore, the search for exoplanets illustrates the power of collaboration across nations, disciplines, and between professionals and citizens alike. It is a testament to the shared human spirit, striving to uncover truths hidden by distance and time. The active engagement of passionate individuals around the world demonstrates that science is most vibrant when inclusive and participatory. Philosophically, exoplanets nudge us toward a cosmic perspective, where the vastness of space and time humbles yet inspires. Recognizing Earth as one among untold worlds encourages stewardship of our fragile planet and deepens the meaning of our existence. The endless quest embodies the very essence of scientific endeavor, a dynamic, evolving journey marked by wonder, skepticism, and the unyielding pursuit of knowledge. Each discovery leads to new questions, and every mystery fuels imagination and inquiry. As the next generation of telescopes and missions rise, promising unprecedented glimpses into alien skies, atmospheres, and perhaps life itself, our exploration continues, ever deeper, ever wider. The mysteries of exoplanets open not closed chapters, inviting humanity to wonder, dream, and reach for the stars. Through this quest, we glimpse the universe not only as a vast expanse of matter and energy, but as a profound canvas for discovery, reflection, and the enduring human story.